Outline. At the beginning, we're going through a review of a familiar simple mechanical wave, a rope that is oscillating. And in this context, we introduce wavelength, frequency, and the special case of a sinusoidal wave function, as you can see, that we can write for the oscillating rope. Also the wave equation, which the wave function is going to satisfy that. As you can see, we have a second order differential equation with a second order derivative with respect to position on the left hand side and a second order derivative with respect to time on the right hand side. By starting with this simple oscillating mechanical wave, we slowly make an analogy to electromagnetic waves. First, we are introducing in which circumstances we can have electromagnetic waves, and we will discover that only if an electric charge oscillating up and down, an electromagnetic wave can be produced. And before going to more details, we will go through some applications of electromagnetic waves in everyday life, like our mobile phone, the power lines of electric current, and etc. Then we will introduce the broad range of electromagnetic spectrum and their application in our life, like radio, microwave, infrared, ultraviolet, X-ray, gamma ray, and visible light. And we will see how different creatures can have different visions based on the different electromagnetic wavelengths that they can perceive by their eyes. After that, we're going through some details about electromagnetic waves, so some characteristic features, and we will see that the electromagnetic waves, as you can see in the picture, consist of an electric field and a magnetic field that are perpendicular to each other, and both should be perpendicular to the direction of propagation of the wave. In this step, we introduce sinusoidal electromagnetic wave, and we will do some basic algebras, as you can see in the picture. We'll go through some details, and we will do some basic calculations, and we will solve an example. Then we will introduce briefly the Maxwell's law, like Ampere's law, Faraday's law, Gauss' law, Faraday's law, and Ampere law, the Maxwell's law, which the electromagnetic waves that are found in nature actually are obeying these laws. So for an electromagnetic wave to be found in nature, or for a wave to be called electromagnetic wave, they should obey these laws. And concluding that these laws impose some limitations on the shape and behavior of the electromagnetic waves as we know them in nature, all by using mathematical calculations. So to have an electromagnetic wave like what we had here, exactly here, these two equations on the top right hand side, for them to be found in nature as electromagnetic waves, they should obey Maxwell's law. So we will go through a very brief introduction to Maxwell's law, and we will see that if we apply the Maxwell's law to this to electric and magnetic fields, we will reach at two equations for the electric and magnetic field, which is just similar to the wave equation that we have found before for a mechanical oscillating rope. And here our analogy between an oscillating mechanical rope and electromagnetic fields is getting completed. And we will move forward and we introduce electric and magnetic flux as well. Actually, we do it before introducing all the Maxwell's law, because knowing the magnetic flux and electric flux, or the quantity of flux, is essential. And also the concept of polarization is going to be studied. Then we go through an example of a laser beam and its electric and magnetic field. So we will solve an example of a laser beam, and we will do some calculations about electric and magnetic fields. By learning so far about electromagnetic waves in vacuum, now we are ready to move forward and study the effect of electromagnetic wave in material objects. So for example, when the light, which is a form of electromagnetic wave, is passing through water or any other material like air or glass, and we will see that we should consequently introduce dielectrics. So we consider only analyzing electromagnetic waves in non-conducting materials, which we call them dielectric. So dielectric is a non-conducting material, so it doesn't have any free electron inside. And there are some properties of dielectrics like permittivity, permeability, dielectric constant, and also index of refraction of a dielectric that we were going to define. And also we bring the example of a simple capacitor with a dielectric in, and we introduce the phenomena of induced charges. And finally, we will solve an example for calculating electric and magnetic fields in different material objects.